Correlation, independent and dependent variables, and the types of correlation. Let's start with a definition. A correlation is a relationship between two variables. The data can be represented by order pairs, X, Y pairs, where X is the independent or explanatory variable and Y is the dependent or response variable. Here are two examples of different types of correlation. An X has a negative linear slope. That is, as the values of X increase, the corresponding values of Y decrease. In our XY axis, points are in the upper left-hand portion of the axis. So as X is small, Y tends to be a large value. X increases, the value of Y tends to decrease. For the positive linear correlation, that trend is reversed. As in the XY plot of the positive linear correlation, there are lots of points in the lower left-hand portion of the plot. So as values of X are small, values of Y are also small. And then as the value of X increases, the Y's tend to increase as well. So we slowly start to increase values of Y as we move from left to right. Scattering of points. As X increases, Y doesn't really tend to do anything. So as it increases, the Y's don't tend to do anything. They can be all over the place. So we notice a large blob of points with no discernible pattern. And so there may be a strong relationship between the variables X and Y, but there's no linear relationship. A curve may occur, or some kind of polygon may be observed. All different types of relationships exist. In this lesson, we want to look for linear relationships. Let's take a look at an example. A researcher conducts a study to determine whether there is a linear relationship between a person's height in inches and their pulse rate in beats per minute. The data is shown below. Display the data in a scatter plot and describe the type of correlation. The data includes the value X of height, and the different heights of the folks sampled are 68 inches, 72, 65, 70, 62, 75, 78, 64, and 68, as well as their corresponding pulse rates. And we'll include the value 90, 85, 88, 100, 105, 98, 70, 65, and 72. Plotting the XY axis gives us values of height in inches on the X-axis and gives us the pulse rates in beats per minute on the Y-axis. Moving from left to right, there is no discernible pattern. The value of Y doesn't tend to increase with X, nor does it tend to decrease with X. This tends to be a situation where we do not see a whole lot of correlation, not a strong linear relationship between height and pulse rate. Now let's take a look at our second learning objective. Learn how to find a correlation coefficient, rho, variables. The symbol R represents a sample correlation coefficient. A formula for R is equal to, in the numerator we have N times the sum of the products between X and Y minus the sum of the X's, the quantity, times the sum of the Y, the quantity. And in the denominator, we have the square root of N times the sum of the X squares minus the sum of the X, the quantity squared, times the square root of N times the sum of the Y squares minus the sum of the Y's, the quantity squared, where N is the number of pairs of data. The population correlation coefficient is represented by rho, and that's the lowercase Greek letter rho. The sample correlation is represented in the formula by the letter R. Let's take an annual contribution data shown here. And the values are 1, 10, 5, 15, 3, 24, and 30. And Y is going to be the annual contribution in thousands of dollars. And the values of Y are 12.5, 8.7, 14.6. Calculate the correlation coefficient. We're going to need to look at a table. The table will need to contain the values of X, in this case, the number of years out of school, the values of Y, the annual contribution in thousands of dollars, a product of the X's times the Y, the value for X squared in its own column, and finally a column for the Y squared values. In this table, I have the values of X, 1, 10, 5, 15, 3, 24, and 30 in the leftmost column, followed by the column with Y, the 12.5, the 8.7, 14.6, 5.2, 9.9, 3.1, and 2.7. The corresponding sum of the X's is 88. The corresponding sum of the y's is 56.7. Its corresponding value of y, so 1 times 12.5 gives us the first value of 12. The xy values are calculated. The sum of the xy's is found to be 435.6, corresponding x and y column. So 1 squared gives us the value 1, 10 squared gives us 100, and again, the rest of the values are found in a similar manner. And the sum of the x squareds can be found to be 1,836. Likewise, the y squareds are going to take the values of y. For instance, the 12.5 squared gives us the 156.25. The 8.7 gives us a 75.69. And again, this is continued on to the bottom of the column. And the sum of the y squareds is given to be the value 587.05. It's the sum of these columns that's used in the calculation of the correlation. So the correlation formula is repeated at the top of the screen, and then the correct numbers are substituted in. So in the numerator of the correlation formula, we're going to take the value 7, which is our n, times the sum of the xy's, which is 435.6, minus the sum of the x's, that quantity, which is 88, times the sum of the y's, that quantity, which is 56.7. In the denominator, we take the square root of n7 times the sum of the x squareds, which was 1,836, minus the sum of the x's, that quantity squared, which is 88 squared, times the sum of the y squareds, the 587.05, minus the sum of the y's, that quantity, that 56.7 squared, calculated to be approximately negative 0.9078. Knowing that correlation coefficients range between negative and positive 1, the 0.9078 is a very strong correlation between x and y. And the fact that it's negative leads us to say there's a very strong negative linear correlation between the number of years out of school and the annual contribution. They tend to be quite tedious. My hope is that you'll be able to use some form of technology to calculate a coefficient of correlation in the future. Here are 4 examples of different types of technology that can be utilized: Minitab, Excel, TI-84+, and StatCrunch. It's important to note here that the technology in this slide utilized a different data set. The data set that was used contained 25 observations, and the resulting coefficient of correlation was found to be approximately equal to 0.979. Each of the technology used came up with the same coefficient of correlation, even though they give you the result to different levels of precision. Now let's take a look at our next learning objective. Let's take a look at using a table to test the correlation coefficient rho. First, we need to determine the number of pairs of data in the sample. Second, we want to specify the level of significance. Third, we're going to find the critical value using a table. Fourth, we're going to decide whether the correlation is significant. And then fifth, we're going to interpret that decision in the context of the original claim. In a previous example, we calculated the correlation coefficient of the number of years out of school and annual contribution to be R approximately equal to negative 0.908. Is the correlation coefficient significant? Use alpha equal 0.01. Number of pairs of data in the sample. This is usually pretty straightforward. In this case, there were n equals 7 pairs of data. Second, we need to specify the level of significance. Well, the problem asks us to use an alpha of 0.01. The third step is to find the critical value. This requires a table. So we go to the coefficient correlation table. We look up the value of n in the table. In this case, we're at n equals 7 pairs, and we match that with the corresponding alpha value that we're working with. In this case, the alpha is 0.01, and we find the critical value of 0.875. We need to decide whether the correlation is significant, and a significant correlation is going to be a correlation that has an absolute value of R that's greater than our critical value. In our case, the absolute value of R is 0.908. Remember, it was negative 0.908, and so we just take the positive equivalent of that, and we find, in fact, that is bigger than the critical value of 0.875. So in this case, our correlation coefficient is significant. Now, what does that mean in the context of this claim? There is enough evidence at the 1% significance level to conclude there's a significant linear correlation between the number of years out of school and annual contribution. I'd go a step further here and say that it's a negative linear correlation. This test for us to do is take a look at different null and alternative hypotheses that we could test. The different alternative hypotheses are rows not equal to 0, rows greater than 0, or row is less than 0. As we've learned in prior videos, the not equal to, the greater than, or the less than alternative hypotheses are going to dictate the type of test that we conduct. If we do a not equal to test and write that as the alternative, the null becomes row is equal to 0. If we're doing a greater than alternative test, we'll use row less than or equal to 0 as the null. And finally, if we decide to test that row is less than 0 in the alternative, our alternative creates a null that is row greater than or equal to 0. We again notice that the equal to component shows up in all three null hypotheses, regardless of which alternative is being tested. The t-test for the correlation coefficient. A t-test can be used to test whether the correlation between two variables is significant. The test statistic is R, and the standardized test statistic is T is equal to R divided by sigma subscripted with the R, which is the standard deviation of the R's, and that's equal to R in the numerator divided in the denominator by the square root of, in the numerator it's 1 minus R squared, and you divide that in the denominator by n minus 2. And that test statistic follows a t-distribution with n minus 2 degrees of freedom, where n is going to be the number of pairs. Now let's take a look at the steps involved using the t-test for the correlation coefficient rho. Thing is to specify the level of significance in the degrees of freedom to fourth, determine the critical value or values, and the rejection region or regions. Fifth, we'll use the data to find the standardized test statistic. Sixth, we'll make a decision to reject or fail to reject the null hypothesis. And finally, seventh, we'll interpret the decision in the context of the original claim. Now let's take a look at an example. Suppose the correlation coefficient of the team's salaries and average home game attendances for the 30 teams in Major League Baseball is approximately equal to R of 0.792. Test the significance of this correlation coefficient, and we want to use an alpha of 0.01 we wish to test. If we're just testing to see if there's a significant linear correlation without specifying positive or negative linear relationships, we're going to conduct a two-tailed test by using a null hypothesis of rho equal to 0 versus the alternative rho is not equal to 0 of 0.01. The third thing we want to consider is our degrees of freedom, errors minus 2, which in the case of the 30 Major League Baseball teams is 30 minus 2 or 28. We then go to the t-distribution to determine the critical values and the rejection region. Again, we're using a two-tailed test, so when we go to the t-distribution, we're going to take our alpha of 0.01 and split it so that we put half of alpha, or alpha over 2 equal to 0.005, in both tails of the t-distribution. Probability of 0.005, we can find the critical values of negative 2.763 and positive 2.763. We use these critical values to determine the rejection region, which in this case will be the value of t greater than 2.763, or a test statistic t that's less than negative 2.763. The next step is to find the standardized test statistic. So now we need to go to the data and take a look at the value of R and the value of N. Right? We're going to take the value of R, which in this problem was given as approximately 0.792, and we'll use that in the numerator. And then in the denominator, we will divide by the square root of, in the numerator, it's 1 minus R squared. So in this case, it's 1 minus the 0.792 squared. And then the denominator is going to be n minus 2, or 30 minus 2, equal to the value 6.86. Now we need to take a look to see if that standardized test statistic is far enough out in the tail, or tails, to reject H naught. It is less than negative 2.763 or greater than positive 2.763. And when we plot the test statistic of 6.86 into the rejection region picture, we find that it is in fact greater than 2.763. So our decision is going to be at alpha equal 0.01, H naught can be rejected. We are able to reject H naught, so we're going to be able to say there is enough evidence at the 1% level of significance to conclude that there is a significant linear correlation between the team salaries and average attendances per home game for the 30 teams in Major League Baseball. Now let's take a look at our next learning objective. Learn how to distinguish between correlation and causation. It does not in itself imply a cause and effect relationship between the variables. Consider the following 4 possibilities. First, is there a direct cause and effect relationship between the variables? That is, does X cause Y? They may be correlated, but that doesn't necessarily imply that X causes Y, so we have to ask that question. Second, is there a reverse cause and effect relationship between the variables? That is, does Y cause X? That would also result in a strong correlation. We need to consider the possibility that Y, in fact, causes X, caused by a third variable, or perhaps a combination of several other variables. Again, just because X and Y are correlated doesn't mean there's a causation. There may be some other variable or a combination of other variables that has a relationship with both X and Y. And then fourth, is it possible that the relationship between 2 variables may in fact just be a coincidence? Just because we see a correlation between 2 variables, it may just be a coincidence and nothing more of causation. Now it's your turn. Take a look at all things related to the correlation coefficient. Be able to calculate, be able to understand what the relationship looks like, and be able to test a correlation coefficient. Also, understand the relationship between correlation and causation. Now, take a look at some of the problems in this section, and good luck.